All right, hello and welcome to Pretext Science. All right, gang, what we're doing today is we're talking about temperature and heat. If you were in this morning's lesson, you learned this, so I'm going over. These are the notes you should have in your notebook. All right, couple of reminders in my notes. I put down questions that I'm going to be asking you guys or that I asked during the lesson, which are squares with little X's around them or inside, and definitions are stars like that. Today we're talking about temperature and heat. Let's get into it. Okay, temperature and heat. A couple of things we're going to be talking about. We got to remind ourselves that kinetic and potential energy. Okay, kinetic energy, KE, is energy of motion, and potential energy is energy of position. Okay, the reason this is underlined is because that's what we're talking about today. We're talking about the energy of motion. All right, when we talk about kinetic energy, all right, that's what we're going to go into. When we talk about temperature and heat, we're talking about the motion of what, you might ask. We're talking about the motion of particles or molecules. You're going to hear me talk about particles, molecules. Don't worry about that. I use those words kind of interchangeably. All right, it's just whatever comes to mind at that point. All right, don't worry about it. So, talking about thermal energy, because that's what heat is. Okay? Heat is thermal energy. We've talked about that when we talked about the 7 different types of energy. From there, all right, now we can say, what is heat? And that was one of the questions I asked to the class this morning. What is heat? Now, a lot of people might say, oh, I see, like a mirage. I see waves rising above the car hood when I'm stuck in traffic during the summer. Okay, I see waves radiating above the hood. Okay, what else? Well, some people might say steam rising above a boiling pot of water. Okay, yep, that's heat also. But what are we actually seeing? Are we seeing the heat? Well, then what is heat? Well, some people say on a warm day, when I'm standing in front of the fridge before my grandma smacks me in the back of the head, my feet feel cold air. Like I feel the air falling out of the fridge and going across my feet, and it's cold air. So then what the hell is heat? All right, well, seeing the movement of those particles, seeing the waves, seeing the steam, maybe seeing the, condensate, for lack of a better word, of the air rolling out of the freezer, okay? Know that when we have faster particles, we have more kinetic energy. All right, so the faster the water boils, the more or the faster the steam rises. We're going to talk about that in terms of what heat is, because we still haven't really defined heat. Thermal energy, or heat energy, is the amount of energy an object or a substance has. The reason I say substance is because we're going to be getting into solutions and liquids and mixtures and things. So substance is actually easier to talk about when we're talking about thermal energy. When we talked about mechanical energy, it was about the object, because we can't necessarily see particles. Thermal energy, we're going to be more often talking about substance, okay? So thermal energy is the amount of energy an object or a substance has because of the movement of its molecules, okay? Because of its movement of its molecules. So, with that said, what's temperature? I asked this during class, what is temperature? Well, what I remember my students saying during that lesson, some people might say, oh, it's hot. All right, temperature, yeah, it can get hot. All right, cold, something that's cold. All right, an ice cube is cold. Well, that doesn't really help us with temperature. What about lukewarm? Who the hell is this guy, Luke? All right, if something is lukewarm, meaning warm, okay. What about room temperature? Yeah, a lot of people say, oh, bring it up to room temperature. Well, what is room temperature? Is that 68 degrees? If it's summertime, wouldn't the room temperature, if you don't have AC, wouldn't it be the temperature it is outside, maybe a little cooler? If it's 80 outside, might be 80 in my room. So what is room temperature? Okay. What we're defining here, if we were to say what temperature is, these answers are actually qualitative measures. We've talked before about qualitative versus quantitative. Qualitative, all right, using words, can be more subjective. What I mean by subjective is one person's hot is another person's cold. What's a good analogy for that? One person's hot is another person's cold. One person's room temperature is another person's hot temperature. Okay, have you guys ever gone to a hotel and stayed in a jacuzzi? Have you ever gone into the jacuzzi? Well, if you go into the pool first, the pool feels nice and warm. You get into the jacuzzi and the jacuzzi's hot. But what happens? After a certain amount of time, the jacuzzi you actually kind of get used to it a little bit. When you were a kid, did you ever go back out and jump into the pool? And the pool is frozen. It is freezing cold. You're screaming like a baby. That water is so cold, but it hasn't changed temperature. It's cold relative to your interpretation of it. It's subjective. If you go back into the jacuzzi, it's hot again and it's burning you. It's subjective. Depends on other factors that are qualitative. Okay, what about Florida? Florida, when it's 60 degrees, people are wearing sweaters. In Vermont, when it's 60 degrees, people are loving life. Shorts, t-shirts, especially in the spring. If it gets to be 60 degrees, I got my windows down, I got the wind flowing over my bald dome, okay? I'm loving it. So, Florida, when it's 60 out, it's cold. Vermont, when it's 60 out, it's hot. It's hot in the spring, it's cool in the fall. Same temperature. It's subjective. I want to talk a little bit about wood versus metal. So you guys probably have, in class, I would ask you to hold on to the legs of your metal table. I would have you grab the metal table, and I would have you grab the wood table top. And I would ask you which one feels colder. And you would say, oh my God, it's the metal table leg. It feels colder. It is colder. I said, well, what temperature is it? And you're like, well, it's probably the temperature of, I don't know, it's cold. Well, why does the wood feel warmer? Oh, the wood is warmer. Well, what temperature is the wood? Well, when I get you a thermometer like this thermometer, and if I was to take this thermometer and touch it to the wood and get the reading of the thermometer of the wood, or maybe I used this instant read thermometer. If I did that, what temperature, if the room is 68 degrees, what temperature is the table? Well, probably 68 degrees. What temperature is the table leg? Well, probably 68 degrees. Why does one feel colder? That's going to be our next lesson, so I want to come back to that. But can we agree that they are both the same temperature? Hopefully you watched the video in the Schoology page, and you noticed that there is a video on heat misconceptions. Those misconceptions led you to what we're talking about next. Now, hot or cold, like we just talked about, is not very precise. It's subjective based on your interpretation. Scientists, they need more precision. We need more precision. Where does that precision come from? It comes from the fact that temperature is the measure of the average kinetic energy of an object. It's the measure. So that means it is a quantitative bit of data. All right, this is quantitative. Quantitative data. Okay? Qualitative means it's a quality, hot, cold. Quantitative means it's a measure, it's a bit of precise numerical value. So, when I say average kinetic energy, what I want to talk about is this thermometer and how it looks at temperature. Okay? If I had, and I often find this, if you've ever had coffee and you have a coffee cup, okay? Let's say that you filled this coffee cup with hot coffee. And I put this thermometer in there and it's reading it's reading, let's say 200 degrees. Okay, this thermometer is reading 200 degrees. Let's say I add some milk to this. Nice cold milk. Pour, pour, pour. I pour some milk in. What happens if I pour it really slow? Do you ever notice? If it goes in, it then comes back and curls up along here if you pour it in fast, and it actually mixes really well. If I didn't pour it in fast and I poured it in slow, like I hit the back of a spoon or it went right down the side, it's going to fill up the bottom. And I wonder if I could get it to stay at the bottom. I wonder if I could get it to sit at the bottom. The answer is yes, and we're going to do, well, I would love to do that in class if we ever come back to school. So what we would see is two different thermal layers, all right? Just like when you open the fridge on a hot day and the fridge is pushing cold air down over your feet, the milk is cold sitting at the bottom of the coffee cup. Hot coffee at the top. If we don't mix it, these thermometers are going to be different. This one is going to be higher, and this one is going to be lower. This one's going to be the temperature of milk. This one's going to be the temperature of coffee. So thermometers measure the average number, the average measure of the liquid or of the whatchamacallit, substance. So if we pour this in, we have these thermal layers. All right. If you've ever gone swimming in the ocean and you swim through, you go down deeper and it's colder. All right. If you are at the top and it's warmer, well, nobody peed there. Well, maybe if you swim through a warm spot, but you get what I mean. It's warmer at the top, colder at the bottom. So hot coffee might be 130 degrees. Cold milk might be 50 degrees if you pour it slow. This thermometer will be showing 130 degrees. This thermometer will be showing 50, even though they're in the same vessel. If we give it time and we mix it, we're going to see a mixture that is in equilibrium. Okay? We have coffee milk or coffee with cream. If we did it half and half, all right, it would be lower than that. There's actually a mathematical function to calculate that based on density and volume. Nevertheless, if we only added a little bit of milk to a lot of coffee, maybe it's around 100 degrees. These are equal. That is the average. It's taking, all right, what we're seeing here is actually a thermometer is only measuring the particles in direct contact or very close to the tool. Well, what is a thermometer? Funny you should ask. I have that right here. A thermometer is a tool that measures temperature. Okay? Last thing I'm going to leave you with is, how does a thermometer work? That's a great question. I asked this of my class, and some of them says, well, the mercury goes up and down. Okay, if it's an old thermometer, or the liquid rises and falls. Okay, in here there's liquid, and if it gets warmer, it rises. What if I turn this upside down? If it gets warmer, it goes down. Or if I hold it sideways, if it gets warmer, it gets righter or lefter. Well, the reason why is because what we're actually seeing is as substances heat up, there's a rise in temperature, or if they lose heat and they reduce in temperature, its particles change their speed. Higher temperature, faster moving particles needs more room to move around. It expands. Lower temperature, slower moving particles need less room to move. They contract. We're going to talk about smooth jazz and rock concerts in the next class. I'm out. Talk to you later, guys. See ya on Wednesday.